Welcome to the 7th learning workshop. Today's workshop is going to be covering solutions. We're all about solutions in chemistry. All right. So the first thing I want to deal with is the principle of solubility. Now, one of the fundamental principles of solubility is the principle of like dissolves like. So I'm actually going to go ahead and type that here. Like dissolves like. Now, there we go. So like dissolves like basically means that if a solute is polar, it will dissolve in a polar solvent. If it's nonpolar, it will dissolve in a nonpolar solvent. And the reason that this is the case is that polar substances stick together much more tightly than nonpolar substances. So if you try to put a polar solute in a nonpolar solvent, the polar solute is going to stick together and it won't break apart. It won't be able to be separated by the nonpolar solvent. Likewise, if you have a nonpolar solute in a polar solvent, the solvent particles, the polar solvent particles, are going to stick together, and they're not going to want to have anything to do with the nonpolar solvent. So it's just the nonpolar solvent and it needs a nonpolar solute, or the nonpolar solute needs a nonpolar solvent to dissolve, because they don't stick together as tightly, so they can easily kind of just mix in with each other. But if you have a polar solute or a polar solvent with a nonpolar, the polar one they're going to stick together too tightly and not allow for anything else to come in. Okay, so if we look at this first example, NaCl, is that a polar solute or a nonpolar solute? What do you think? Yeah, it's polar. So it's a polar solute. In fact, it's extremely polar because it's ionic. Ionic is polar to an extreme degree. Basically, what polar means is that, and actually I'm going to go ahead and write this on the page, but essentially, when we say polar, we mean that one side of the molecule / substance is more positive and another side, usually the opposite side, is more negative. Okay? Now, usually these partial positives and positives and negatives are partial. Now, actually, I'm going to put that down. Usually, these positives and negatives are partial, meaning that they represent a fraction of the charge of an electron or proton. They're not a full electron's worth or a full proton's worth of charge. They're just a partial or a fractional amount. However, in ionic compounds, the charges are full charges. A full +1 or a full proton worth or a full electron's worth. Where is it? Hide that. Okay. Or a full electron's worth of charge. In the case of ionic compounds, sometimes more, because it can be +2 or +3. Okay, so based on this, yes, this is extremely polar, and therefore, will it be soluble in water or will it be soluble in CCl4? Water, exactly. So this will be soluble and insoluble. Okay, what about I2? Do you think that's going to be polar or nonpolar? Yeah, nonpolar. Why do you think that's the case? It, it does actually have valence electrons. Now this is a tricky question. So why do we know it's polar or nonpolar? Essentially, what it comes down to is this: I2 is a two-atom molecule. You have iodine bonded to another iodine. Each iodine has the same pull or the same attraction for electrons. So because it has the same attraction for electrons, it's since they have the same attraction for electrons, neither one is going to pull more strongly than the other, and they'll be evenly distributed, and therefore it'll end up being nonpolar. So as we mentioned before, that means of course it'll be soluble in CCl4, but in water it will be mostly insoluble. Iodine doesn't dissolve very well in water. Now, um, it is tricky because to really understand the rules of polarity, we have to dig a lot deeper into chemistry than your course actually goes into. So, but generally, the type of questions that I've seen from professors for your 1406 class generally limit nonpolar substances to things that are common. So, like for example, it's commonly understood, it's commonly known that water is a polar substance, more negative on one side and more positive on the other. Because the polar nature of water has been taught to you probably every year since you were in fifth grade. But um, and olive oil, we know that oil and water do not mix. Well, that means that if water is polar, that means olive oil must be nonpolar. And there's a general understanding that fats tend to be nonpolar. The only type of molecules that they'll probably give you as far as solutes to determine if it's polar or nonpolar would be two atom molecules. Because for two atom molecules, the polarity of the bond is the polarity of the molecule. And so how can you tell if a bond is polar? Well, if the atoms are different, if it's not the same atom, then it's going to be a polar bond. So like for example, in I2 it's the same atom, so they have equal poles, and it's going to be equally distributed, the electrons will, and therefore it's going to be nonpolar. However, if it was HCl, those are two different atoms, and so therefore that would be polar. Or if it gave you something like NO, what do you think? Would NO be polar or nonpolar? That's a little bit trickier because they're close together. What do you think? If you had the compound NO, nitrogen bonded to oxygen, would that be polar or nonpolar? And actually, it might surprise you to know that it would be polar. Because even when atoms are relatively close together, like nitrogen and oxygen, there's still a difference in electronegativity. And in most cases, that difference in electronegativity is going to be large enough that it's going to be cause the bond to be polar. So in this case, uh, this is ionic or superpolar, uh, uh, ah, green leaf, polar. Um, Iodine, of course, we know is going to be nonpolar. And we already kind of talked about this. Olive oil is going to be what? Polar or nonpolar? What do you think? Nonpolar, exactly. Because it's a fat, and fats are nonpolar. And what about sucrose? Sugar.
Polar.
That's going to be polar. And one of the ways you know sucrose is polar is because, one, you know that sugar dissolves in water pretty easily, doesn't it?
Yeah.
And so, let's say this is definitely soluble in water. What do you think? Is it going to be soluble in CCl4?
Soluble.
Nope. Actually going to be
Non-polar.
insoluble.
Insoluble. Hmm.
Yeah, because the sucrose is polar, but CCl4 is nonpolar, and therefore they are not alike. Like dissolves like. That's the principle of solubility. So if CCl4 is nonpolar, it will not break apart sucrose. The sucrose is a very polar molecule. And in the case of organic compounds, which this type of thing might be asked of you at some point, actually, let's go ahead and type this out. So this is insoluble. We know it's not uh, soluble that. And this will be soluble in CCl4. Let's go. I'm going to go ahead and add another row below. I'm going to add another one. If you let's say you have an alcohol, let's say we have like CH3. Whoops, what the that CH3 CH2 OH. So this is alcohol. This is actually specifically ethanol or drinking alcohol. This is the one present in wine and beer and other things like that. So whenever you have an OH, is that going to be polar or non-polar? What do you think?
Hydroxide.
Yeah, that
Non-polar.
could be. Actually, anytime you see an OH in a non-metal compound, or rather in like a non-metal compound, that's going to tend to make things polar. And the reason is because it provides what are known as hydrogen bonds. I don't know if you talked about the different types of intermolecular forces and hydrogen bonding yet in this course, but anytime you have an OH or an NH, that's that's hydrogen bonding, and that's going to cause things to be very polar because the OH bond is a very polar bond in and of itself. So is it going to be soluble in water or insoluble? What do you think?
My question is, how do you know soluble and how do you know insoluble? I want to believe that soluble is the one that just follows water, right? And
Well, the principle is like dissolves like.
mm,
So if the solute is polar, then that means it'll only dissolve in a polar solvent. So which of these two, water or CCl4 is polar?
I think it's water.
Yeah, water is the polar one. It's actually labeled right here. So that means of these two substances, which is ethanol going to dissolve in? It's going to
Water.
dissolve water. It's going to dissolve in water. And that makes sense because if you think about it, wine is not mostly alcohol. It's only about 10% alcohol. The rest of it is water.
Water.
And if you have like something like a real strong rum, well, that's going to be about maybe 50% alcohol, but it might be a little higher, but it's not going to be too much higher than 50%. Um, and so once again, uh, it's going to be half water, and so they're very soluble in each other. Water and ethanol are very soluble in each other because they both have hydrogen bonding actually, but that'll be insoluble in CCl4. I think we've kind of beaten that one to death, so we're going to leave that alone for now. Let's take a look at number 5. This is where we talk about solubility. Now, when we refer to the solubility of a substance, The solubility of a substance is basically its, um, when we say solubility, we're referring to the maximum solubility. In other words, this is the maximum amount that can dissolve at that temperature. So at 22 degrees Celsius, the maximum solubility of KNO3 is 34 grams per 100 milliliters. If a solution contains 66.4 grams of dissolved KNO3 in 187 milliliters of water, is the solution saturated or is it unsaturated? So, and it says if the solution is saturated, how much remains undissolved? So in a problem like this, the easiest way to deal with this is to determine what is the maximum amount that could dissolve in the given amount of solute, or solvent rather, given amount of solvent. So if I'm looking at the amount of solvent given in this solution, the solubility is the one that's shown on top, but that's not the solution I have. The solution I have is this 187 milliliters of water, okay? That's how much I have. I want to figure out how much KNO3 can dissolve in that much water. So one of the things that I would do here is I would set up a ratio. Okay, so on the one side of the ratio, I'm going to put my solubility, 34 grams KNO3. Actually, I'll use the appropriate subscript just so it looks fancy. And the other one, that's 34 grams of KNO3 that can be dissolved in 100 milliliters of water. The water, of course, is H2O. On the other hand, on the other side, I'm going to go ahead and put my 187 milliliters of water, which is the amount in my actual solution. And I'm going to try to solve for the amount that could dissolve in that much water. So now we can go ahead and do our cross multiplication. Do y'all know how to do cross multiplication? Solve for x. Okay, sure, no problem. Okay, so for cross multiplication is basically just a simple way of uh, simplifying the algebra, so to speak. In when you have two fractions that are equal to each other, I simply multiply the top of one fraction with the bottom of the next, and the top of the other fraction with the bottom of the first one, and then from there I get an expression of in this case I'd have the 34 grams of KNO3, and I'd be multiplying that times 187 milliliters of water, which is the bottom of the other fraction. And then I would take my x on the other side, and I'd multiply that times the 100 milliliters of water on the bottom of the other fraction. That's called cross multiplying. Yeah. It's a way to simplify fractions so that you don't actually have a fraction anymore. You no longer have a denominator. That's good because that helps us to isolate the variable. Now in this case, the variable I want to isolate is x. So if I want to solve for x, I have to get rid of the
Divide
100
by both sides.
milliliters. Yeah, exactly.
100 equals
So I
to
divide both sides by 100
63.58.
milliliters.
63.58.
63.58.
Mm-hmm.
Very good. I'm going to go ahead and write this down. Now, one of the things you'll notice here is that the milliliters of water cancels out. On the left side, the milliliters, the unit cancels out. Not the numbers, but the unit. So yeah, 34 times 187 divided by 100. As Linda said, it gives you 63.58 or is that correct? 63.58 or 63.6? So X here ends up being 63.6 grams. Now this is the maximum amount that can dissolve. And notice it's grams of KNO3. And this is based on the solubility. The solubility represents the maximum amount that can dissolve. So this is the maximum that can dissolve. If that's the case, if that's the case, is the solution saturated, unsaturated, or supersaturated? Or rather, is it saturated or unsaturated? That's right, your course does not deal with supersaturated. Assuming that this is the maximum amount that can dissolve, anything beyond this will not dissolve. It'll just stay in the solution. It'll just stay as a solid. So is this solution saturated or saturated or unsaturated rather? What do you think? Saturated. Absolutely, that is correct. Oh, whoops. Basically, the idea here is that the amount in the problem that it says we have added to, the amount added is this. We have this much added. Ah, okay. Um, There are 66.4 grams that are added. However, the maximum that can dissolve is 63.6. So if a solution has the maximum amount that can dissolve, then it's a saturated solution. Anything that you add beyond that will not dissolve, but it will stay as a solid. So in this case then, to figure, it says if the solution is saturated, how much of the solute remains undissolved? Well, how would I calculate that? How would I calculate that?
Subtract?
That's right, subtract. So what would you subtract? Exactly, man. It's 66.4 minus 63.6. You take the amount that you added minus the maximum that can dissolve. Very good. And if you subtract those, you end up getting 2.8. So 66.4. And please forgive me if I'm going a little bit slow. I just want to make sure that I'm making sense to everybody. 2.8 grams. This is the amount of KNO3 that remains dissolved. Or that remains undissolved, rather. Cool. So let's go ahead then and take a look at the next problem. Well, there we go. It says if enough sodium nitrate is dissolved in 456 milliliters of water to make a saturated solution at 25 degrees Celsius, how much more sodium nitrate must be added to make the solution saturated at 60 degrees Celsius? And it says use the solubility table below. use the solubility data below. So in this case, we make a saturated solution at 25 degrees. And we have to find out how much more has to be added to make the solution saturated at 60 degrees. So for this, what we're going to want to do is we're going to want to solve for how much would be present in a saturated solution at 25, and then how much would need to be present for a saturated solution at 60. And so this data here, we can actually set up two equalities just like we did before and solve them just like we did before. So let's first start with the saturated solution at 25 degrees Celsius. So I'll start with my solubility at 25 degrees Celsius. 90 grams of solute can dissolve in 100 grams of water. So I'm going to put 90 grams of NaNO3, which is my solute. Ah, oh, there we go. In 100 grams of water. And on the other hand, how much solution do I have? Or how much water do I have in this case? How much water do I have in this solution? Yep, 456. So I'm going to put that amount down here. And I'll be looking for the amount that can dissolve. I'll be looking for that amount to make a saturated solution. And so then let's go ahead and cross multiply for me and tell me what you get. Very good. Now, did anybody have any trouble getting that answer, the 410.4? Whoops. For significant figures purposes, I might just stop this at a whole number. I might just stop this at 410. But yeah, 410. Whatever. 410.4 grams. We're not paying close enough attention to sig figs right now. That's okay. We're not supposed to take sig figs till the very end anyway. So then, okay, cool. So now let's go ahead and we'll do a similar calculation. However, this time we want to figure out what would be present for a saturated solution at 60 degrees. So I have to change the solubility. Instead of being 100 or 90 grams per 100 grams of water, it's 125 grams per 100 grams of water, because that is my solubility here at 60 degrees Celsius. So now I'll do the same process and I'll cross multiply again, but I'm going to get a different answer. And what answer do I get? Good job, you guys are fast. 570. Got some good consensus there too. All right. Yeah, 570 grams of water. Or no, I mean of sodium nitrate, NaNO3. So we made a saturated solution at 25 degrees Celsius, which means we used 410.4, or roughly just 410 grams of sodium nitrate. However, if we wanted to make it a saturated solution at 60 degrees Celsius, how much more would we have to add? Well, we know we need to get up to 570. So we can just take our 570 minus our 410. And that means to get a saturated solution, we would have to add at least 160 grams of sodium nitrate. Does that make sense? Now, just as a side note, another thing that you could do here is you could actually use your solubility as a conversion factor if you wanted to. I could say I could have started with my solution. Well, I have 456 milliliters of water, and I could use my solubility as a conversion factor. And I could say, well, 100 milliliters, well, 100 milliliters, 100, yeah, 100 milliliters, 100 grams, 100 milliliters of water, 100 grams of water is going to give me 90 grams of sodium nitrate, or it's going to allow me to dissolve 90 grams of sodium nitrate, NaNO3. And I would get the same answer. I just multiply the top divided by the bottom, and that gives me 410.4 once again. So that's another way to do it.
Michael,
Yeah?
I would have thought that the water would be up so that it can cancel out with the 100
Yeah.
gram.
So that's actually, it's a good point, and I really should have brought it up. Um, Here's the deal. Now, this is water in both cases. Uh, and this is something that I'm not sure if it's kind of just expected that you know, but essentially the density of water, I don't know if you remember the density of
Is one.
water is 1, exactly. The density of water is basically 1.00 grams per milliliter. Because of that, for water and for water only, milliliters and grams are interchangeable. So 100 grams of water is 100 milliliters of water. 150 grams is 150 milliliters of water. So water, milliliters and grams are interchangeable.
I know. What I'm saying is that how did you cancel out the water? You didn't cancel it out? No?
I did. It's just it says it's 456 milliliters, which, like I said, milliliters and
Okay, I
grams are,
get you. Okay, I get you. Thank you.
yeah,
It's okay. I saw it.
yeah. There you go. So you could use it with a conversion factor, or you could use the ratio method. Either one of them is perfectly acceptable. Feel free to use whatever one makes more sense to you. Okay, so let's look at number 7. The next thing we're going to be dealing with in the solutions chapter is concentrations. And so you're going to have to know how to calculate concentrations and to use concentrations as conversion factors. When you're given concentrations, you can use them as conversion factors. When you're asked to solve for them, then you're going to have to use the formula for it. So it says percent mass volume. So for percent mass volume, specifically in this case, if I want mass volume percent, and it's typically given like this, percent mass volume like that, it's basically going to be the grams of solute over the milliliters of solution times 100%. Now this isn't a perfect percent because grams and milliliters are not necessarily interchangeable, but this particular, the mass volume percent, assumes that grams and milliliters are close enough for the purposes of this particular calculation that they are almost interchangeable. So what I would do is I'd take this formula and I would simply plug in my information. So I have grams of solute, 30 grams goes on top, right? And then I have milliliters of solution that gives me as 150. So then I just multiply that times 100%. And if I plug that into my calculator, that should give me 20%. Does that make sense? Cool. So let's go ahead and try the next one. Now in this case, it actually gives me the concentration. Now, percent, when I hear the word percent, what does that mean? What does percent mean? It means per what? Per hundred, exactly, out of 100. Like the Latin word for hundred is centum, and like if you think there's 100 cents in a dollar, there's 100 years in a century. So cent means 100 in this case. So percent means out of 100. So when I see this, I can transform this into a conversion factor. I can say, well, it's a mass volume percent, so that means it's 12.0 mass, which is a unit of grams, over out of 100 milliliters, which is a unit of volume. So this is my conversion factor. So I have to be able to recognize that when I see 12.0%, that's 12.0 grams per 100 milliliters, because it's mass over volume. Now, if I want to figure out how many grams of NABR are needed to make 2.4 liters of solution, what I'm going to have to do is I'm going to start with the 2.4 liters after I recognize my conversion factor. What's the first thing that I'm probably going to have to do with this unit of liters? What do you think? Convert to milliliters, exactly. Because this percent, mass volume percent, is for milliliters, not liters. So I have to convert the liters to milliliters. So I'll put liters on the bottom, so it cancels, and milliliters on top. And how many milliliters are equal to a liter? Or, not quite. How many milliliters are equal to a liter? 1,000. You could, so there's actually two ways to do this. Milli does mean 0.001, so 1 milliliter is 0.001 liters. But alternatively, you could also say that 1,000 milliliters, I'm actually going to put that in a different color. This green one, this will work. I could also say 1,000 milliliters is equal to 1 liter. See, the ratio is still the same. It's the top is still 1,000 times bigger than the bottom. Milli does mean 0.001, but if you're going to use the meaning of the prefix, make sure you put a 1 in front of your base unit. Just make sure the top is equal to the bottom, because we know that the liter is a larger unit, so there should be more milliliters for every 1 liter. I'm going to go ahead and simplify this. We're going to just put the one of them. I guess I'll go with 1,000 milliliters is equal to 1 liter. Yep, there we go. So now that we have the milliliters, now we can use our concentration as a conversion factor. I'll put 100 milliliters on the bottom, and I can convert that to grams of NABR. And how many grams? How many grams is it going to be? What do you think? How many grams is it going to be? There, yep, 12.0. It's 12%, so it's 12 grams per 100 milliliters. What happened to my little guy? Okay, there it is. 12.0 grams per 100 milliliters. Okay, so then I multiply everything on top, divide by everything on bottom, and if I do, I should get what? 288, very good. So this will give me 288 grams of NABR. Yay, cool. Now, the next problem is a percent by mass problem. And these can be a little bit tricky because instead of having clear units of one versus the other, like milliliters is always the unit of Sir's solution for mass volume solution, and grams is always the unit of the solute. But here we have grams for everything. So you really have to pay attention to your wording here. 20-gram sample of sodium nitrate is dissolved in 75.3 grams of water. What is the concentration of sodium nitrate expressed as percent by mass? So first of all, let's look at what the solution, what the equation is. So the equation for percent by mass, or mass percent, very similar to that of mass volume percent. It's just the mass of the solute, or in this case, the grams of the solute. I'll just simplify it by putting grams. Grams of solute divided by the grams of solution. Okay? Times 100%. I apologize for my sloppy writing. Okay. So what are the grams of solute here? Which one of these is the solute, and how can you tell? Which one of these is the solute, and how can you tell? Yeah, it says the 20 grams is dissolved. So yes, that definitely is the case. Now, it is possible for the lesser amount, it is possible for the lesser amount to be the solvent, but usually the amount that is in the greater quantity is the solvent. So in this case, water is the greater amount, so that would be your solvent. Usually that's how it works. But also the key word is dissolved in. So the solute is always dissolved in the solvent. So good eye on that. All right. So you know that the 20 grams is a solute. So what's the solution then? How many grams of solution do we have then? What do I put on the bottom? No, not 75.3. Why is it not 75.3? It feels like that's what it should be. It seems like that's what would make sense. It says grams of solution. Is 75.3 the grams of solution?
Are you supposed to use the no periodic table?
Mm-mm. See, the solution is composed of the solute and the solvent. The solution is both the solute and the solvent. It's both of them together. So if the solution is both the solute and the solvent, then that means that we have to add the two together to get the mass of the solution. So in this case, it would be the 20 plus the 75.3, so 95.3.
Oh, wow.
Does that make sense? Solution. Yeah, the 75.3 is just the solvent, and I need both the solvent and the solute. Both of them together to give me the solution. So then if I go ahead and divide 20 by 95.3 and then times 100%, what do I get?
20 divided by 95.3.
Times 100. And Leanne sounds about right. I think it's about 21.0% mass to mass. Very good. Very good. There would be three significant figures because each of our numbers is 3, say 6. And we're dividing. All right, cool. Now let's try number 10. In fact, actually, would you all like to take a stab at number 10 on your own, and then we can kind of come together after you've had a chance to work it out? What do you think?
No.
No, you don't want to. You don't want to try by yourself. You want to just go over it together.
Yes.
Okay. All right. How about the rest of you? Do you all feel like you'd rather do this together? What do you think? I'm not seeing anything in the chat. Okay. All right. So it sounds like the consensus is let's do it together. Okay. So once again, anytime you see a percent by mass or a percent concentration, that means you have a conversion factor, right? So 35.3% by mass. What does that mean? If I wrote that as a conversion factor, what would I write? 35.3 what?
Gram.
Grams. And specifically grams of solute. In this case, it's HCl is the solute. And it's percent, so that means it's over what?
33.3 points.
It's over 100. Yeah, that's right. So 35.3%. So 35.3 out of 100. So the 100 will be on the bottom. And the 100, it's percent by mass, so it's 100 grams. And it's 100 grams of what? 100 grams of what?
HCl.
Not HCl. Because remember, percent always refers to percent always is the part divided by the whole times 100. And the whole thing is what?
Water.
Solute? Is it the solution? Is it the water? What is it?
Water.
Total solution?
It's the total solution. Not just the water, it's the whole thing. So the 35% always refers to per 100 of the solution. Percent is always per 100 of the solution. So up here when we have the 12%, this is 100 milliliters of solution. When we have the 35.3%, this is 35.3 milliliters of the solution. And the solution is the water and everything dissolved in it. The whole thing. And it doesn't even have to be water, it could be something else. Because you can dissolve things in like alcohol, you can dissolve things in gasoline. Whatever you're dissolving something in, that's the solvent. And the whole thing, all the stuff in there, that's the solution. Okay, so now we have a solution. This is our conversion factor. And this is how many grams of HCl would need to be bubbled into water to make 950 grams of total solution. Well, if this is my conversion factor here, and I'm going to start with, well, the only thing I can start with, I can't start with the conversion factor. The only thing can start with is the 950 grams of total solution. So then I'll take my 950 grams of solution, And then I'm going to have to set up my, use my conversion factor to convert to HCl. Excuse me. So what unit goes on the bottom? It goes on the bottom of this conversion factor.
Solution?
Yep, the grams of solution. And how many grams of solution?
950?
No,
Oh, 100.
nope. 100. There you go.
Yeah.
Although in fact, I made a mistake though. Well, I broke my own rule, shall we say? My own rule for doing conversion factors, and that is always put your units first before you put any numbers. What am I converting this grams of solution to? What unit should go on the top?
The
Water?
mass.
Not the water. Linda, I think you were about to say something.
35.3% by mass.
The mass of what?
HCl.
The mass of HCl. So I'm going to put the grams of HCl up here. And therefore, how many grams of HCl?
35.3.
Exactly. 35.3 grams of HCl can dissolve in every 100 grams of solution. So this is my concentration that I'm shooting for. The grams of solution cancel out. And if I multiply everything on top and divide by the bottom, what do I get?
950. 335.35.
335.35. You know, somebody got something slightly different. Oh, okay. Yeah, okay, yeah, that. Okay. So 335.35. Or in this case, because it's only really,
335.
yeah,
Three significant figures.
yeah, three significant figures. And technically it only be two, but that's okay. We're going to go with three. 335
Grams HCl.
grams of HCl. Now, if that's the case, if it's 335 grams of HCl, it says how much water would be needed. Well, if I know there's 950 grams of total solution, and I know that 335 of those grams are HCl, how much water is needed? How would I figure that out?
Divided by 100.
No?
I just said it. Like, I
You
don't know.
subtract?
You have to subtract them. So
Oh,
this,
shit.
because the solution is the solute and the solvent, right? It's both of them together. If I know how much of this is solvent, or solute, in this case 335 grams of solute, then that means what's left over, this is the HCl solute, what's left
235.
over is going to be the solvent, or the water. And yeah, that's going to give me 615 grams of solvent, or water. Does that make sense? Bam. Cool. So now that we've done now we've done some problems with percent concentration. There's also some volume percent concentration, but it works the same way as percent mass. So it's all pretty similar with these percent concentrations. They're pretty straightforward as long as you understand that the percent means that the mass volume percent is grams over milliliters. That anytime it refers to mass, it's grams. Every time volume, it's milliliters with these percent concentrations. And that you can use them as conversion factors if you're given the concentration. Molarity is a little bit different. Molarity actually is the most common unit of concentration for chemists, and molarity means moles of solute per liter of solution. solute per liter of solution. Now, in the case where you're given molarity, we can use molarity as a conversion factor, and I'll go through with you how you would actually do that. However, in this first case, we're actually asked to solve for the molarity. So it says, what is the molarity? For that, I'm simply going to use this equation and follow a relatively simple three-step process. To get the molarity first, I find moles.
But I would have thought we should convert the 750 to liters first. What do you think?
It actually doesn't matter what order you do steps 1 and 2.
Okay.
Step 1 is find the moles. Step 2 is find the liters.
Okay.
I want to say find, I mean calculate. Sometimes they're given. Find the liters. And then 3, divide moles by liters. Divide moles by liters. Okay, so step 1, I'll calculate the moles. And to do that, I'm just going to do a similar process to what you learned in a couple chapters ago. I'm just going to convert the grams to moles using what?
Moles is volume times molarity, right?
Well, no, if I'm converting grams to moles, what do I do? Where do I go to find that relationship? You actually
The periodic
mentioned
table.
periodic table. There you go. I was going to say, yeah, you actually mentioned it earlier when we were talking about it. Yeah, when you want to convert grams to moles, I have to use the molar mass from the periodic table. And what is the molar mass of NaOH?
Let me check.
1 sodium, 1 oxygen,
Oxygen is
and 1
16. Hydrogen is
hydrogen.
1.008. And then sodium is it 12 point? No, I don't think so.
Sodium's on the far left side, third row down.
Is that 12.01? No, I think that's carbon.
22.99 is the mass of sodium.
Sodium is what,
Is the
2.1?
total 40.01?
Yeah, or
Oh.
and honestly about 40.00, but yeah, 40. I mean, yeah, it'd be about 40.00. I mean, 40.01 is okay too. But basically, the molar mass of sodium hydroxide is almost right about 40, and that's really nice actually for us. We can just go ahead and calculate this, and that's going to give you what? It's about 0.125 if I'm calculating that correctly in my head. That's the moles. And I actually made a little mistake there. I put a capital M. Moles is lowercase m. Did anybody else get 0.125? Okay. So there we go. Yeah, I'm not crazy. Well, I may be crazy, but at least I'm not wrong. All right, cool. Now I'm going to find liters. Let's go ahead and do the same thing. I'm going to convert milliliters to liters. This is a conversion you're probably all familiar with at this point. Just multiply times the 1,000 milliliters is equal to 1 liter. In this case, that means I'm dividing by 1,000. And that's going to give me 0.750 liters. So then all I have to do to calculate the molarity is divide the moles by the liters. And that's 0.125 moles over 0.750 liters. And what does that give you? 0.167, very good. We have 0.167 molarity. And a full answer would be 0.167 molarity NaOH. Because we want to know not just what the molarity is, but also what it is of. I just have a bottle that says 1 molar. That's great. It tells me the concentration, but I don't know if that stuff is going to eat my hand off or if it's something that's relatively benign. So I got to figure out what exactly that 1 molar is of. In the lab, we always label our things not just with the concentration, but the substance. So a full and complete accurate answer would be 0.167 molar NaOH, sodium hydroxide, which in fact will eat your hand off. Did you know that? Sodium hydroxide will actually eat away your skin. Fortunately,
How corrosive is it?
very corrosive, extremely corrosive. Um, in fact, at first it'll just make your hand feel slippery because it's dissolving your skin.
God
But
forbid.
if you
You
leave it
deserve
on,
your
yeah, if you leave it on your skin for a few minutes and you don't do anything about it, your fingers will start to feel sore because all of your outer skin has dissolved and it's starting to touch upon the nerves. And the
That's an
nerves,
acid. That's an acid now. That could be an acid burn.
well, it's actually bases are worse than acids in many
Jeez.
senses because bases like the NaOH, you don't feel them when you get them on you, so you don't think to do anything about it. An acid, if it touches you, it burns. Like you feel the burn, and you like immediately. I mean, just the natural instinct is to go ahead and rinse it off. But a base, you don't feel anything. It just feels slippery. So it just so you don't think to get rid of it, and by the time you do get rid of it, the damage is already done. By the time you start to feel something hurting, you've already gotten a significant base uh, burn, so to speak, or
Wow.
yeah. In fact, not sure if I should be telling you this. I guess it's available on television too. But I mean, if you wanted to dissolve a dead body, concentrated NaOH will actually leave nothing, not even the bones.
Whoa.
Yeah. Sure.
Hmm.
Yeah.
That's not working.
Don't get any ideas. Don't don't you put that back in the bottle. Um, okay, so now let's look at for example number 12. And in the case of number 12, it says how many moles of LIBR are needed to make 50 liters of 1.25 molar LIBR solution. So 1.25 molar LIBR solution. So this molarity here is given. You have the molarity. And when you're given molarity, that actually makes your life a lot easier because when you're given the molarity, you can use it as a conversion factor. So when I see 1.25 molar, I can break that into its conversion factor form. I can write it as 1.25 moles over 1 liter, or moles per 1 liter. Just like if I'm driving a car at 70 miles per hour, or 100 kilometers per hour, if I'm driving a car at 70 miles per hour, I'm going to travel 70 miles in 1 hour. Well, likewise with molarity, 125 moles per liter is 125 moles per 1 liter. So I can use this as a conversion factor. I can also flip it. I can also put 1 liter on top and 1.25 moles on the bottom, depending upon what I'm looking for. In this case, the other number that I'm given is 50 liters. So I would go ahead and say, okay, well, I'm going to take my 50 liters, 50.0 liters, okay, 50.0 liters, And I'm going to convert this. I'm going to go ahead and set up a conversion factor. And what unit is going to go on the bottom?
Liters.
Liters. And what unit can I put on top? What can I convert liters to?
Milliliters?
I could convert liters to milliliters, but
Grams?
that's not going to help me get to moles of LIBR that I'm looking for. What can I convert liters
Moles?
to?
Moles.
Moles, exactly. Moles of LIBR. So I can convert liters to moles of LIBR, and the reason I can do that is because I have that conversion factor, the molarity. So what goes in front of moles? What number? Yeah, 1.25, very good. 1.25 goes in front of moles. And what goes in front of liters? 1, very good. 1.25 moles per 1 liter. Basically, I'm just taking this guy over here and I'm putting it right here. And now all I have to do is multiply everything on top and divide by the bottom, and if I do that, I will get 62.5 moles of LIBR. Yay! We're so cool. Alright, so now, would you like to give problem number 13 a try? Or do you want to work that one together? What do you think? How brave are you?
H2SO4. Where's my periodic table?
Alright, good. Go forth and give it a try. And once you have an answer, or once you think you have an answer, go ahead and raise your little hand sign. That's the little guy on the bottom. The, right next to where you mute yourself or turn on your microphone. Yeah, you can just hit the little raise hand. You can also raise your hand if you give up and you just are going to wait until we go over it together. But so raise your hand if you have an answer or if you get stuck, basically. And we'll go over it together once we see some hands raised.
Is it 147?
Linda, you're not supposed to give the answer.
Is that what? Huh?
I got that answer too.
No, that sounds actually pretty good. That actually sounds pretty good. Let's go ahead and let's go over it. Since Linda let the cat out of the bag. All right, so we're going to do 750 and milliliters. We'll go ahead and okay. So 750 milliliters. I'm going to convert it to liters, right? Because of course our 2 molar, that is going to be written, that can be written as a conversion factor, 2.00 moles of H2SO4. H2SO4 over 1 liter. That's what that conversion factor means. Or that's what that 2 molar means, 2 moles per 1 liter. So I need liters, so I have to convert the milliliters to liters. There's that one extra step here. Once I have liters, then I can bring liters down here and use my conversion factor, the molarity, to convert the liters to moles. And then, of course, it's 2 moles for every 1 liter. And then the moles of H2SO4 comes down on the bottom. And then it can convert to grams. And this is probably the one that might have been a little tricky for you to recognize you had to convert from moles to grams. But yeah, converting from moles to grams, you're going to have to use the molar mass. And I believe if you calculate it properly,
It's 98.079.
yeah, it's going to be about 98.08 exactly. Is going to be 98.08 grams is equal to 1 mole. Yep. So
Sorry.
there you go. Well done. Well done. And then you multiply everything on top, divide by the bottom, and that should have given you about, what did you say it was, 147?
147.1, but you just say 147.
Yeah, it'd be 147 with 3 sig figs, because if we look at our 3 numbers that have sig figs, our initial number has 4, but our concentration only has 3, and our molar mass is 4, so we have to go with the lowest one, which is 3. So there'll be 3 significant figures, 147 grams of H2SO4. Well done. I'm super proud of you guys. You nailed that. That's awesome. All right. So now I want to take a. There's not much left that we're going to go through, and we don't have much time anyway. But I do want to actually talk to you about electrolytes, strong electrolytes, weak electrolytes, and dissociation. So strong electrolytes can be one of two things really. So something is a strong electrolyte if it is a strong acid. And I don't know if you have know your strong acids yet, or if you've memorized them.
It
But your
has only ions.
yeah, strong acids are strong electrolytes and ionic compounds.
Yeah.
Those are the only strong electrolytes there are. And I should actually emphasize that the ionic compounds do actually need to be soluble. Because there are some ionic compounds that are not soluble and therefore they would not be strong electrolytes. Alternatively, the weak electrolytes, uh, those would be your weak acids and bases. So these guys,
I think they contain both molecules and ions.
well, yeah, it contains both molecules and ions. But if you're trying to identify what, if something would be a, if something would be a strong electrolyte, a weak electrolyte, or a non-electrolyte, well, your strong electrolyte is either going to be a strong acid or an ionic compound, and your weak electrolytes are going to be weak acids or weak bases. Uh, so weak acids and weak bases.
Is it and or?
And yeah, and so and weak bases. So weak bases or well, it would be or really, because something's not going to be both a weak acid and a weak base at the same time. It's going to be one or the other.
Exactly.
So weak acids or weak bases, those are going to be a strong, are going to be your weak electrolytes, and the non-electrolytes are primarily just going to be your molecular compounds. Okay. So the
Yeah,
non
yeah, only molecules.
yeah, they tend to be like just your molecular compounds. So
When they
if
say
we,
they are non, when they say they are non-electrolytes, what do they mean? It means they don't
I
have.
mean, they don't break up at all. When you put them in water, they don't break up into ions at all. Okay. So, for example, let me show you an example with the electrolyte equation. NaOH, this is a strong electrolyte. It's an ionic compound. It also happens to be a strong base, but it's an ionic compound. So when NaOH is dissolved in water, this is what happens. NaOH does not stay, it does not stay a solid when it's dissolved in water. Instead, it breaks apart into separated Na plus ions and Cl minus ions. Oh, sorry, not Cl minus, I mean OH minus. OH minus ion. Na plus ions and OH minus ions. So that's what a complete dissociation looks like. It's going to completely separate into its separated ions. Now, if you're looking at the substances below, if you look at acetic acid, well, there's a list of 7 strong acids, and anything other than those 7 strong acids is a weak acid. And I'm actually, because you're going to actually need to memorize them anyway, especially
Hmm?
for the next chapter on acids and bases. You're going to need to memorize your strong acids. There's only 7 of them. I'm going to go ahead and list them right here for you, just because I'm that kind of guy.
uh,
HCl,
HCl, strong acids. Right. Okay,
uh-huh,
let me write.
uh-huh, HBr.
Could you go back again, please? Sorry.
Oh yeah, I'm writing it on the page. You can see it, right?
Okay, strong
So
acids. Okay.
HCl, HBr, HI, um, H,
Hydrogen iodide.
yep, exactly. HNO3, HClO3, HClO4, and the last one is the only one with 2 acidic hydrogens, and that's H2SO4, otherwise known as sulfuric acid. So HCl, HBr, HI, HNO3, HClO3, HClO4, and H2SO3. So if I'm looking at
SO3 or SO4.
H2SO4, sorry.
Mm.
So if I'm looking at the acetic acid down here, I can see that acetic acid is vinegar, by the way. And you can see that this is clearly not a strong acid. Acetic acid is not a strong acid. It's not one of the 7. It's actually pretty weak, which is why you can actually drink it and it won't kill you. Um, Not that you want to drink vinegar. But since
Can
this
be
is a weak
diluted in
acid,
drink.
yeah, since this is a weak acid, this would be a weak electrolyte.
Weak.
And because it's a weak electrolyte, it's going to be mostly molecules with a few ions. I'll put few ions as an abbreviation. So what about a solution of glucose? What about this one? Is that going to be only ions, mostly molecules with a few ions, or only molecules? What do you think?
First of all, is that an electrolyte? Glucose.
Well, that's the question. Is it an electrolyte?
It does. It does. Uh, yes.
Oh, Linda says yes. Yes.
I know that salt is an electrolyte. I'm not sure of sugar though.
I'm looking at glucose now, right?
Mm,
Is glucose ionic?
I'm not sure.
Okay. Does it have a metal in it? I see C, H, and O. Are any
No,
of
it
those
doesn't have
metals?
a metal.
Okay, so it's not ionic then.
No,
Does it have, is it an acid?
no.
No. So it's not ionic and it's not an acid, so it cannot be a strong
It's
electrolyte.
a electrolyte.
Yeah, it's not a
Electrolyte.
weak acid or a weak base, so yeah, it's not actually an electrolyte.
It's
It's a
not, yeah.
molecular compound. And if it's a molecular compound, that means it's non-electrolyte. So what is it going to be? Ions,
Not electrolyte. It has only molecules.
only molecules. That's right. This is only going to be molecules.
They give glucose to people who are, athletes when they run, they give them glucose just to give them energy. So it cannot be acidic or anything.
Yeah, exactly. Um, Now what about NaI? Is that ionic or
That's
covalent?
that should be an electrolyte.
Yeah,
Any,
NaI is an ionic substance because sodium is a metal. So
yes,
this
it's
is going to be only ions.
ions.
Because yeah,
Yeah.
this is a strong electrolyte because it's an ionic compound.
Mm.
What about HF? What about this guy?
Should
Is
that
that
be a weak
strong?
one?
Oh, very good. How did you know it was a weak electrolyte?
Hydrogen.
Because it has an acidic hydrogen, but it's not one of those strong acids, right?
No, it's not.
So because it's an acid but not a strong acid, it has to be a weak acid, and therefore it would be a weak electrolyte. It would only contain
Uh,
it would be mostly
Molecules with a
molecules,
few ions.
exactly, molecules with a few ions. Few, sorry for my sloppy writing. Few ions. Hey, cool. Good job. So would this equation here represent a strong electrolyte, a weak electrolyte, or a non-electrolyte?
Strong electrolyte because it has sodium.
Well, it would be strong because you have to actually, in this case, when you're basing it on an equation, you want to look at this. Okay,
It
so
still has sodium in it.
that arrow is only one directional. So because that
Oh,
arrow is one directional, this is strong.
oh, I see.
Likewise with the next one, even if you were not given, even if you didn't remember anything about what a strong electrolyte was, you look at this, you see it does separate into ions and the arrow is only in one direction. So that
Mm-hmm.
would tell you this is what type of electrolyte.
Strong.
Strong. Now, if it was a weak electrolyte, what would you see?
It will go both sides because it has both ions and molecules.
Exactly. So it might look something like this. And you'd have like an H plus and an F minus. But there would be arrows in both directions. Very good. And the last thing I'm going to cover is super easy, so I'm not going to spend a whole lot of time on it. There's this concept known as equivalent in chemistry. And it's not used terribly often, but it does show up in your book. And for some reason, some professors want you to know it. But an equivalent, one EQ or one equivalent is effectively 1 mole of charge. And it doesn't matter if it's positive or negative charge, but it's 1 mole of charge. Okay? So if I'm looking at this, for example, 21, 2.4 moles of magnesium, well, magnesium has a 2 plus charge. So how many moles of charge would that be?
Say it again.
There's 2.4 moles of magnesium, but
Mm-hmm.
every magnesium has a 2 plus charge. So
Mm-hmm.
how many moles of charge would there be in 2.4 moles of magnesium?
Would you
We should
multiply 2.4 by
multiply.
2?
Mm.
Exactly. You'd multiply 2.4 by 2, and that would give you 4.8 equivalents. 4.8 moles of charge, or 4.8 equivalents. What about the 1.25 moles of iodine? How many equivalents would that be?
It
Just
would say 1.25.
Yeah,
1.25.
exactly, because the charge is only -1, so it's just 1.25 moles of charge because it's 1.25 moles times the charge of 1. So very good. So as you can see, it's a pretty simple concept, right? Not too complicated. We'll do one more just for fun. What about the 0.75 moles of aluminum?
3 times 0.75.
And that would give you?
I don't know.
2.25.
0.25.
Yeah, 2.25 equivalents. Very good. Well, you guys are set to go. Excellent. And we've run out of time. I guess I could have gone over hypertonic, hypotonic, and uh, isotonic solutions, but it looks like we're not going to have time for that. But that's fortunately not too difficult of a concept. So, um, have any of you covered any of the solution stuff yet?
In class?
Yeah.
In class, we're doing chapter 8, 9, and 10, right? And that's what we're doing for the next exam.
Okay.
Yeah, so we are doing gas now, gas and bases and all of that now.
And then solutions, and then acids and bases next. Okay.
Yes, that's what we're doing for this next exam in April.
Okay. Well, next week we're going to be going over acids and bases, so we'll have you set.
I really wish we could do gases again, though. You know, when we taught it, when you were teaching it the last time, it was not yet time for us to take it.
Well, remember, you can always go back and you can look at the recorded sessions because I have those posted up on our website.
Oh, that's
Um,
true.
so yeah, and just in case anybody uh, uh, needs any help with that, it's also in your email. It's also in
Mm,
your email. Copy. Let me paste this. But
mm,
in the email that I keep sending, I always put a link to the old workshops. You can always check them out there, but you can also check them out here. And that has, if you click on that, it'll take you to all the previous workshops. I'm also going to post the answer key to this, the one that I've just posted here, just because I think it will be helpful as well. I'll post that up on the website. I haven't posted it yet, but I will. Um, all right, cool. Well, thank you so much for coming. Appreciate it. And it was good seeing all of you again. Um, I will see you next week.
thank you.